What's up, guys? So it's Declan, and today I want to do a life cycle analysis of a wind turbine. So first, the specs of the turbine I'm analyzing, it's the GE 1.5S, which is the most popular model in the US, and it has a blade length of 35.5 meters, rated wind speed of 13 meters per second, and tower length of 80 meters. And for this, I want to analyze how long it'll take for the operation of the wind turbine to pay back all of the carbon emissions it took to manufacture. So to start, I want to determine the electrical power and the force of the wind on the turbine. So to do that, I use actuator disk theory, where V1 is the wind speed, A is the area, and V is the speed of the wind going through the turbine. So I started with the equation force is equal to mass flow rate times change of velocity. And then at any point in the disk, mass flow rate is equal to A times the velocity times the density. So then I derived that the force is equal to the density area times velocity times the difference in velocity exiting and entering the wind turbine. So then from actuator disk theory, we derived the Betz limit, which is basically the maximum efficiency of the turbine. And that happens when V2 over V1 is 1/3, and V is the average of V1 and V2. So plugging this in, I got the force was 360 kilonewtons. And then using power is force times velocity, and plugging in the above assumptions, I derived the power was 3.1 megawatts. But in reality, turbines only reach 70% of the Betz limit. So multiplying these values by 0.7 gives F is 250 kilonewtons and power is 2.2 megawatts. So next, I want to analyze the thickness of steel used in the wind turbine tower and the CO2 produced from manufacturing the turbine tower. So first, I estimated the tower diameter. So the height is 17 times more than the base diameter, and the average diameter is about 3/5 of the base diameter. So then on average, the diameter is 3 meters. And then I analyzed it as a cylinder in cantilever bending. So then the max stress is the moment times the distance from the neutral axis, which in this case is just R, divided by the moment of inertia, which I derived, as you can see here. And then I set the max stress equal to the yield stress over the safety factor, and assuming a safety factor of 2 and yield stress of 240 megapascals, I got the moment of inertia is F times L, where L is the length of the beam, times D, where D is the external diameter, times the safety factor divided by 2 times the yield strength. And then, so I got that that moment of inertia was 1/4 of a meter squared, and plug it into the moment of inertia equation, derive the thickness of the steel is 0.05 meters. So with that thickness, I wanted to generate the total mass of the tower, because we now know that 1.85 tons of CO2 are produced for each ton of steel for this particular manufacturing process. So assuming that the tower is a conical shell, we can just multiply the surface area times the thickness times the density. And then from that, we got the mass of the tower is 288 tons. And so the mass of CO2 is 1.85 times that, which is 530 tons. So yeah, that's all the problems that I've done so far. But in the future, for this project, I'm going to analyze the total mass of CO2 that it takes to produce the wind turbine blades, and do a similar cantilever beam analysis with composite materials and distributed loads. And then I'm going to do an analysis using cost of transport to determine how much carbon it will take to move all the turbine components to the site. And then I'll also do an energy analysis to determine how much power and how much CO2 will it take to move all of the components to their final location in the air. So yeah, thanks for listening, and let me know if you guys have any questions.